Yes. So I hope you have studied this DC to DC converter in your theoretical in your theory class. Okay. But still, I will give you some hint about DC to DC converter in order to understand a particular Simulink model for DC to DC converter. Okay. So if you have any doubts, you can ask me at any time for the previous classes. Okay. And while yes, this is so in today's class we will see DC DC converter. DC DC converter. Okay, so this is what the block diagram I'm drawing. So this is my DC DC controller or converter, DC DC converter, and at input side I'm having DC supply. Okay, so DC supply, but DC supply is not regulated, so I'll write it as unregulated. Okay, likewise we have seen in terms of you can say rectifiers. Okay, so rectifier, what it does, it will convert your AC into DC. Okay, but if you see that output waveform, so it is not a regulated, it is not a proper, or okay, so this is what unregulated DC power supply or DC supply, which is given input to your DC to DC controller, and then output of this DC DC converter will get an regulated DC power supply, regulated DC power supply. Okay, so so why this DC DC converter is required? In order to get a regulated DC output voltage. Okay, so input is not regulated. Okay, if you see that DC DC controller, input is not regulated. For example, if you talk about a mobile charger, we talk about mobile charger. What is that input at the mobile charger? The input is your AC signal, or you can say unregulated AC for the mobile charger. Okay, so in order to get a DC supply at the output, okay, what we do, we will use a rectifier circuit. Okay, so I will draw, this is my AC input, and that to be unregulated AC input. This is fed to the a rectifier block. This is fed to a rectifier block, and that rectifier block will give me an unregulated DC supply. Okay, so it will give me unregulated DC supply. Okay, and then unregulated DC supply I will feed to this unit, that is my DC DC. Okay, DC DC converter, and at the output of this DC DC converter I will get an regulated DC power supply. Okay, so example is mobile charger. Likewise, in a mobile charger we will have that AC input unregulated voltage supply. Okay, and then we feed that to rectifier, and rectifier output is unregulated DC supply, and that output we will feed to DC DC converter. Okay, there are various DC DC converters are there. Okay, we'll talk about this, and then in the after output of DC DC regulated, we will get a regulated DC power supply. We'll get a regulated DC power supply. What I am talking about regulated DC power supply means, we have seen that IC 7805. Okay, 7805 LM, I think. Okay, LM 7805. It is your voltage regulator. Okay, or it is called as linear converter, or it is called as linear converter. So if you talk about this unregulated DC supply, so in unregulated DC supply we'll get you can say there are multiple of ripples. Okay, ripples in terms of your current and your voltages. Multiple ripples in terms of your current and voltages. Okay, and the output of this DC DC converter, we have very low ripple voltage. We have very low ripple voltage and low ripple current. Low ripple current. Okay, in order to reduce this ripples voltage, okay, and ripple current in your rectifier circuit, we will use this DC DC converter. Okay, we will use this DC DC converter. Okay, just hold 1 minute. Is that clear now, this DC DC converter, or any doubts are there? Okay. Okay, in terms of waveform, if you see that, okay, in terms of waveform, Okay, so we'll have this, you can say this is what my sinusoidal AC waveform. Okay, and then at the output I will get this kind of, you can say, ripples. Okay, this kind of ripples. Likewise, I will get a DC voltage, that is V minimum or V maximum. Okay, one more thing that we need to consider while in DC converter. Okay, that is the switching frequency. Okay, so switching frequency, if we talk about switching frequency, if the switching frequency is low, okay, if the switching frequency is low, then we'll get an high ripple, and if the switching frequency is high, then we'll get a low ripple. Okay, this is important, switching frequency, when you're going to design when you're going to design your DC converter. Okay, when you're going to design your DC converter. So one of the example which I will take in terms of DC converter is the buck converter. Okay, is the buck converter. Just hold 1 minute. Okay, let me open the diagram. Okay. Okay, so I will draw the buck converter diagram. Okay, so yes, I will use white color. Mhm. This is what my capacitor is, and then we have the switch. Okay, switch, or you can say the device, that is your SCR. Then we need a diode, then inductor, and then one more capacitor. Okay, and then this is, I will take at output. Okay, okay, so this is my switch. I will take this as name as S. Okay, what are the switches? So switches, like in buck converter, we can use a MOSFET, metal oxide semiconductor field effect transistor. We can use IGBT. Okay, then we can use your GTO, SCR. Okay, likewise switches are there. So in this particular example, okay, when we design our model for buck converter or DC converter, we will use MOSFET as a switch. We will use MOSFET as a switch. Okay, so depending, yes, how do we select which kind of switch is there? So depending upon your applications, or depending upon the cost effectiveness. Okay, that we need to choose this parameter. Okay, likewise your inductor also. Okay, likewise your inductor also. So this is my switch, and this is my capacitor. Okay, this is my capacitor, and this capacitor, across this I will get an input voltage. Okay, this capacitor is meant for filtering out the input, you can say filtering out the input. Okay, so input, it will act as an input filter. It will act as an input filter. This is my switch. This is the diode. So that is my freewheeling diode. This is my inductor. Okay, and then voltage across this inductor is VL. Okay, so so this inductor helps us in order to get the smooth output current. In order to get the in order to get the smooth output current. In order to get smooth output current. Okay, this inductor. What is the use of this capacitor? This use of this capacitor in order to get a smooth output voltage. Smooth output voltage. Okay, this capacitor helps in filtering the input. Okay, then this is the switch, this is the inductor. So value of inductor depends upon what is the smooth output current is there. Okay, so it will help in getting the smooth output current. This capacitor helps in getting the smooth output voltage. Okay, is that clear? Okay, and then yes, then I think we have this. I will write it here. Variety of MOSFETs are there. Okay, if you go to the MOSFET, okay, also there are variety of MOSFETs. So variety of MOSFETs, you can say variety of ranges are there. Variety of ranges. So you can choose it accordingly. Okay, variety of MOSFETs or variety of switches are there. You can choose a particular switch depends upon, you can say the cost. Okay, depends upon the cost or depends upon the variety of range. Fine. Now, if you see the operation, okay, maybe you have studied this, but I will explain you what is the mode of operations. Okay, so this MOSFET works in the two mode of operations. Okay, so it has two modes. So I will write this as my mode one. Okay, so in mode one, if you see that how this current is flowing. So in mode one, this will be on. This your switch will be on. In mode 1 your switch will be on. Okay, I will redraw this, or this MOSFET has been closed. Okay, so this is what, and then this inductor, and then the capacitor. There is a freewheeling diode is here, and then there is a capacitor this. Okay, and I will get an V in at this side, and then V out. Okay, so this S is on in mode 1. S is on in mode 1. So if S is on in mode 1, how this is the current direction? So current will flow from this direction. Okay, switch is closed, so it will go from this inductor, and then it goes towards this capacitor, and then it goes to your negative side. Okay, negative supply. Okay, likewise the flow of current. Okay, whenever your switch is on or your mode 1 is there. Okay, so whatever at the input side, so at input side I am having unregulated DC supply. So this is at my input side, that is my V in. Okay, and yes, of course, how this switch is run. When we yes, that switch, we need to apply PWM pulse. We need to apply PWM pulse. Okay, so here I will say that this is what my PWM pulse output is there. Okay, that is on and then off, on and off. Okay, so this is my output of PWM. So this is on, this is off. Similarly, this is on, this is off. Okay, so based upon your TS, okay, that is sampling time. That is sampling time. So just re-editing this. Okay, and then if you calculate the current, okay, so during the, you can say PWM on, or during the on period, your current will increase. Okay, your current will increase, and then it goes to decrease while off period, again it goes to increase. Okay, so likewise waveform is there in the mode 1. Okay, similarly if you see the mode 2, where your switch is in off position, so I will redraw this circuit. Okay, so here this is my switch and it is in off condition. Okay, there is a freewheeling diode is here, and then capacitor is also there. Okay, this is my capacitor. Yes, capacitor, this is D, this is capacitor, and then I'm having this inductor, and then we have this capacitor across this. Okay, this is connected. So this is what my capacitor is there. and then at this I will get an output. Okay, so this is my VE. So your switch is off. So this is my mode 2. Your switch is off. That is my mode 2 of operation. Okay, so if my switch is off, so there is no flow of current in this circuit because this is an open circuit. Okay, so no current is flowing. But whereas if you see that in the earlier case it was switch is on, so some current, so current has been passed. Whatever current that is stored in this capacitor, so capacitance energy is dissipated. So what is that energy is there? That energy stored in the capacitor is dissipated via the diode. Okay, so current will flows in this direction and it will goes to this direction. So whatever that current is there, that is from your you can say capacitor. So energy stored. So capacitance energy is dissipated in diode and again it goes to your load. Okay, again you will get that load current. Okay, in this mode 2 operation. Okay, so in mode 1 that switch is on, in mode 2 switch is off. How is this? You will get current at the load. So because of the switch is on, this is what the current path. Okay, and in this case in the mode 2 the switch is off. So what is the direction of the current? So here there is no current in this direction, but whatever that energy stored in the capacitance, so capacitance energy is dissipated across this diode and again you will get an load current. So in this direction. Fine. So I hope you are clearing about this mode 1 and mode 2 operation of your DC-DC controller or converter. Okay, so how these current conduction modes are there? Okay, we'll talk about current conduction mode. Current conduction mode. Okay, so there are two types of mode. One is called as continuous current conduction mode and one is called as, other one is called as discontinuous mode. Okay, so yes, I will draw this continuous mode and then discontinuous mode. Okay, so continuous mode means we have that electromagnetic load or you can say inductance is there. Okay, in discontinuous load we have a resistive type of load. We have a resistive load here in discontinuous mode, and in continuous mode that is where we can say electromagnetic load. Okay, electromagnetic load, or you can say that inductive load. Inductive inductive load. Fine. Okay, so for continuous, if you see that, so I will draw an waveform. Okay, so this is in terms of your current I, okay, which is flowing through that circuit, and then we'll get across this T. Okay, so yes, so this is my T on time. Okay, and then T off time. Okay, so if you see that in current conduction mode, okay, so this is what you can say T of time. So my current is decreases here and again it start increases and then decreases. Okay, so this is my output current. Okay, so it varies across my T and T of time, and which is in the continuous type of, you can say, mode. So continuous mode, where it is used whenever my load is electromagnetic load or wherever my load is inductive load. Okay, what about discontinuous mode? In discontinuous mode, if I am having a load like resistive type, then I can use this in terms of discontinuous mode. So what will be the output waveform for discontinuous mode? So in discontinuous mode, this is what you can say that I will draw. This is my current direction, and if there is break of this current also, okay, when there is a break, okay, so here you can say that your inductor current, okay, so current across this IL is equals to 0 in this particular uh, you can say area. Okay, and whatever that we have defined it here for T on and T off period, that will be the same. Only the case is that in terms of resistive load or in terms of our load is resistive, so we can go for discontinuous mode. In discontinuous mode, your current in some time, okay, your current at some instance of time, it will be zero. Okay, so there will be you can say there will be no so even if there is no current in some time, okay, and if your load is resistive load, then your DC-DC converter will work. Okay, but in terms of if inductive current, or you can say inductive load or electromagnetic load is there, so that there should be a continuous mode. Okay, it should be in continuous mode. There should be no disruption of the current which is flowing through your inductor. This is what the meaning. Okay, so what we have seen, I will just go to back again. I will read out what is that particular thing. So we talked about DC-DC converter in today's class. Okay, then what is DC-DC converter? The DC-DC converter which convert your unregulated DC power supply to a regulated DC power supply. This is what the meaning, or this is what the you can say work of DC-DC converter. Okay, we talked about an example of this mobile charger also. I will give you that AC input at unregulated. So, okay, at the mobile charger, and then we use rectifier circuit. So rectifier circuit will convert my AC to DC. Okay, AC to DC, but that DC is unregulated DC. So that unregulated DC supply I will pass, unregulated DC I will pass to DC-DC converter, so that I will get an regulated DC power supply. Okay, then switching frequency is important in order to consider the DC-DC converter. So if switching frequency is low, I will talk about DC switching frequency in terms of designing of you can say buck converter. Okay, so switching frequency, if it is low, then high ripple will be there. If it is high, then low ripple will be there. So it is inversely proportional. Okay, so switching frequency is inversely proportional to your ripple current and ripple voltage. Okay, so that is what. And then this is what the example of buck converter. Okay, so switch we have used here, and then we have this capacitor which is used to filter out the input. This switch is there. So switches can be MOSFET, it can be IGBT, it can be a thyristor, it can be a GTO. Okay, then inductor is used here in order to get a smooth output current, and this capacitor is used in order to get smooth output voltage. Okay, so how to select MOSFET? So depends upon the how to select switch, depends upon the variety of ranges. Okay, then there are two modes of operation. One is your switch is on, and other one is switch is off. And then we talked about the current conduction in this particular both the modes. Okay, that is mode 1 and mode 2. Okay, so when yes, and then we talked about the current conductions modes. So there are two conductions modes, like continuous mode and discontinuous modes are there. Okay, just we have talk about this. Then I will explain you about the various types of DC-DC converters. DC-DC converter. So what are the various types of DC-DC converter? One DC-DC converter. Okay, I will define this as linear converter first. Linear converter. Okay, so this linear converter is also called as load dropout regulator. Likewise, you have this LM7805, or yes, I will write the example 7805 or LM7812. Okay, 7812, and various what are the that regulator, voltage regulator ICs are there. Okay, which will give me an linear curve. Okay, that is linear converter, or you can say linear DC-DC converter. So example is 7805. It is also called as load dropout voltage regulator. Okay, again, if you go further, this linear converter. Okay, so there are two types of linear converters are there. Like one is a series linear converter, and then parallel parallel regulator, series regulator, and parallel regulator. Okay, like IC7805. This is my series regulator. So depending upon the constructional you can say details, it is defined. Okay, series regulator or parallel regulator. Okay, so this is first type of DC-DC converter, that is linear converter. And then we have second, that is hard switched converter. Okay, and then soft switching or switched converter. Okay, linear converter, hard switch converter, and soft switch converter. Okay, so again this hard converter is there, that is again defined as and non isolated isolated and non isolated. Likewise your mobile, your laptop charger. Okay, so this comes in the hard switch converter. Okay, hard switch converter. So what is the difference between hard switching and you can say soft switching? Okay, hard switching and soft switching. Now if you apply PWM, okay, if you see this particular circuit, okay, that is buck converter. Okay, how, when this will conduct? Only when we apply PWM at the gate. Okay, when we apply PWM, that is pulse width, okay, to the gate. Okay, so if we apply PWM, then and then only it will get connected. Okay, so we have that connection, that is your drain to source or collector emitter, anode to cathode, likewise connections is there. Okay, and if you remove that PWM, okay, if you remove that PWM, then it will be off. So your switches are there. Okay, it will have you can say a gate pulse we are providing to this switch. Okay, and when we apply PWM, it will get connected, and if we remove that PWM, okay, so it will act as an off condition. Okay, likewise if apply PWM, then it will be on. If we do not apply PWM, it will be off. Okay, so there are two stages. One is on stage. Okay, so I'm coming to that point. There are two stages. One is on stage and another one is off stage, depending upon the PWM pulse. Either it is on, it will be off. There are two stages. One is on stage and other one is off stage. There is one middle stage is also there, which we call it as a transient stage. Okay, transient state. So in transient state, okay, you can see that there is power loss. If you talk about power loss, okay, so in the transient state there is more power loss. In the transient state, more power loss is there, or it may be have a less power loss. Less power loss. So whenever we talk about more power loss is there, that is my hard switching. That is called as hard switching. If less power loss is there, that is my soft switching. Hard switching and soft switching. So DC-DC converter, three types of DC-DC converter. One is linear converter, hard switch converter, and soft switch converter. What is hard switch converter? In the transient state, if more power loss is there, that is called as hard switching. In the transient state, if less power loss is there, that is called as soft switching. Okay, so okay, so is that clear? Hard switching and soft switching. So I will remove this now. Let us delete this. So if you understood this, hard switch converter and soft switch converter. So you can see that in the hard switch converter, we have two types of converter, that is isolated and you can say non-isolated converter. Okay, isolated or you can say non-isolated converter. So isolated converter, okay, I will, okay. So if you see this isolated converter, so isolated converter are of you can say two types. Isolated converter are of two types. Okay, isolated converter. Okay, so what are the types isolated converter? Okay, I will talk about you can say non-isolated. So non-isolated converter, we have this buck converter. Okay, then boost converter, buck converter, boost converter, or you can say buck boost converter, and then Cuck converter. So this is my non-isolated type of converter. Okay. Uh, uh, then we talk about isolated type of converter. So isolated type of converter we have, that is a single switch, swingle switch. Okay. So this is what the first, and then we have multiple of switch, multiple switch. Isolated converter, there are again two types, further classified as a single switch and multiple switch. Single switch are again further classified. The single switch are again further classified as your buck. Okay, as your buck converter, boost converter, then flyback converter, and then forward converter. I'm not going to deep. Okay, this much details. Okay, you can look into the theory class of your you can say these converters. Okay, then multiple switches. So multiple switches we have again reclassified as half bridge. Then it is full bridge, and the third one is your push pull converter. Is your push pull converter. So again we have this kind of topologies are there. Okay, so likewise example I will take as you can say isolated converter, like a mobile sorry, your laptop charger. Okay, so what is there inside your laptop charger is your SMPS. Okay, so 230 at input side, and then you will get an output at 20 volts. So there will be no any, you can say, physical circuit is there. So everything which will be in your isolation type, which everything which will be there in the isolation type. So likewise here you can see that this is what your linear regulator. Okay, like your 7805 IC is there. Okay, and you can say that this is, you can say, hard switched or non-isolated type of converter is there. Maybe you've seen in some of the circuit boards in your laptop motherboard or somewhere else. Okay, and then this is your isolated power supply, which you can see in your computer, in your you can say uh, laptops. Okay, this kind of isolated power supply in your charger. Okay, in your charger. Then these are the topologies are there, and then we have different kinds of ranges are there. Okay, we have a topology, and then we have different kinds of ranges are there. Likewise, if you see that, okay, so topologies are like single switch flyback, two switch push pull, active clamp, flyback, single switch forward. Okay, two switch forward, half bridge, ZVS. Okay, what is this ZVS? ZVS is nothing but zero voltage switching half bridge. Okay, zero voltage switching. Okay, also there are zero current switching. Okay, ZVS and ZCS, that is zero current switching. And then full bridge, and then phase shifted ZVT full bridge. So depending upon your range, okay, again I'm talking about depending upon range. If you have this power as 100 watt, and if you require that current, that is output current, which is less than 10 ampere, you can go for this. You can go for this kind of topology. Okay, if you have this around 400 to 1200 wattage, so you can go for this kind of topology. If you have more wattage, okay, that is 1200 to 3000, so you can go for this phase shifted ZVT full bridge. So depending upon your topologies, okay, based upon your range, choose the particular topology. Choose the particular topology. Fine. Again, I will go for this. You will get to know about hard and soft switching. So what is hard and soft switching? Again, I will explain in terms of your you can say voltages and current curves. Okay. So Okay, so if you see that this is my voltage curve, okay, and this is the time for my t of time, okay, that is off switch. Okay, so this is my voltage curve. Okay, if my voltage which goes from that is your peak, and it will go down to 0. So here my voltage is 0, here my voltage is 0, and then it will start the current curve. Okay, so this is voltage curve. I will better I will go for this is straight line, consider. Okay, and then we have a second curve. Okay, yes, so this is my voltage curve, and this is my current curve. Okay, this blue color line is voltage curve, this blue color line is, okay, yes, oh, sorry, this is also a voltage curve. Okay, and this is my current curve, and this is again the same, the current curve. Okay, so now what is ZVS switching, that is my zero voltage switching, or what is my ZCS switching, that is zero current switching. Okay, so if you see that this is my voltage curve, and my voltage is during this t of time, so this is my t of time. Okay, so my switch is off, so my voltage goes on reducing, and at one point it goes to 0. So here my zero voltage switching is there, ZVS switching. Okay, zero voltage switching. So if you see this current, okay, if you see this current, okay, whenever my voltage going down, okay, and it goes to 0, and then my current is increases. So this is called as, you can say, hard kind of switching. This is called as hard kind of switching. And if before my voltage goes to 0, likewise here if you see that this dashed line, okay, if you see that this is dash line, so this is called as my soft switching. Okay, likewise here if you get that, if you see that current, so current goes down, and at some point it goes as 0. Okay, so this is called as my, and when my, and that at that particular point my voltage is increases. Okay, so zero current switching is there, that is ZCS. Okay, and if it goes start, if it start before your current reaches to 0, likewise this. Okay, so that is called as my hard switching, sorry, soft switching, soft switching. Okay, hard switching and soft switching, this is what the difference. Okay, so voltage reduced to 0 and then current increases, voltage reduced to 0 and then current increases, this is what I will call it as soft switching. And if the current increases before, you can say, voltage, this is called as my hard switching. This is called my hard switching. Now 12.4 is there, we can go for a model. Okay, we can go for a model first right now. So when is your what is your next class timing? Is that started? Design. Okay, so before going for buck converter, okay, we will see some of the design calculations. Okay, so that we can, based upon our design calculations, we can use that buck converter for buck converter, design calculations for buck converter. Okay, now for example, I will take my input voltage, and that is minimum input voltage, at the buck converter is 16. Okay, and then input voltage, that is maximum input voltage, is 24. So my unregulated DC supply, okay, when I'm talking about unregulated DC supply, so it will fluctuate between 16 to 24 volt. It will fluctuate, that is V in minimum, that is 16 volt, V in maximum is you can say 24. Then output voltage, or nominal output voltage, nominal output voltage is my 12 volt. So I will get at input at 16 to 24 volt, but at the output I must get an 12 volt DC supply. Okay, and then maximum current is also there. Maximum current, that is 2 amperes. Maximum current, that is 2 amperes. Okay, and then efficiency is there. Efficiency is there. So efficiency is 90%, or in numbers I can write it as 0.9. Okay, 0.9. So efficiency is 90%. Okay, now we need to calculate the duty cycle, or you can say maximum duty cycle. Okay, maximum duty cycle. Okay, it is represented in terms of D max. Okay, so maximum duty cycles, how it will be calculated? It is depends upon output voltage divided by V in maximum. What is the maximum input voltage? Multiplied by efficiency, multiplied by your efficiency. What is output voltage? Output voltage, that is your 12 volt. Okay, this is what your output voltage, 12 volts, and then divided by V in maximum. What is the maximum input voltage? That is 24, divided by what is the efficiency? 90%. Okay, so my D max now 0.56. D max is my 0.56 maximum duty cycle. Okay, and the next calculation is we need to find out inductor ripple current. Inductor ripple current, which will be calculated as 0.2 into maximum output current. Maximum output current. What is my maximum output current? That is my 0.2 into maximum output current is 2 ampere. So inductor ripple current, okay, which we can see that inductor ripple current, that is delta IL. Okay, if you see that particular formula for calculation of inductance and calculations of output capacitance, okay, there we will use this term. Okay, I will show you that also. So inductor ripple current delta IL is nothing but 0.2 to multiply by 2, that is 0.4. Okay, what does this mean? That means 20 to, you can say, 40% from output current. This is what the ripple current. What is the ripple current? Ripple current is around 20 to 40%. Okay, because we got the value, that is 0.4. Fine. Also, we need to calculate the desired output voltage ripple. So output voltage ripple, okay, that is defined in terms of delta V out. What is that? That is nothing but 0.6 volt. Now in order to find out the equation, okay, what is the equation for L? Equation of L is nothing but V out multiplied by V in, that is to be maximum V in, okay, minus V out divided by your inductor ripple current, that is delta IL, multiplied by your sampling frequency, multiplied by, sorry, it's not sampling frequency, it's switching frequency. Okay, switching frequency multiplied by 24, multiplied by 24. So yes, here we need what is the switching frequency. Okay, I will write it here. Fs is my switching frequency. Fs is my switching frequency. Fine. So now make the calculations. We know the value of V out, we know the value of V in max, we know the V out, we know the delta IL. Okay, that is inductor ripple current. Okay, that is I ripple. Okay, then we Fs, sampling frequency. So in this case, we will use the switching frequency Fs. In this case, we will use a switching frequency Fs is equals to 5000 only for designing this buck converter. Okay, so Fs is equals to 5000. We'll put all the values. Okay, so V out, that is my output voltage, is 12 multiplied by V in maximum. So maximum will be 24 minus V out is 12 divided by delta IL, that we have calculated, that is 0.4. Okay, multiplied by switching frequency is 5000 multiplied by 24. Okay, just wait. It's not here I mentioned that is 24. It's your V in max. Okay, so V in max is my 24. So this will calculate me L. So L will be equals to, if you can make the calculations of this, so we'll get at 0.003 Henry. Okay, which is equals to 3 millihenry. So L value we have calculated. Now it is difficult to get a particular value inductor. Okay, so most of the times what you have to do is you have to use, or you have to make your own inductor. Okay, so depending upon terms how to make an inductor, that if required I will also explain you about how to make an inductor, particularly about a particular value. Okay, maybe Rao sir will tell you about this, how to make an inductor. Okay, about a particular value. Likewise, here L is equals to 3 millihenry. Some standard inductors are available, but if you want inductor to be a specific value, you have to make it design for yourself. Okay, you have to make it design for yourself. So now we got L. Now we will calculate the output capacitance, that is my C out, which is nothing but the formula is delta IL divided by 8 multiplied by switching frequency multiplied by uh, output ripple. Okay, that is my delta V out. So which is equals to 0.4 divided by 8 into my switching frequency is 5000 multiplied by my delta V out. So what is the value of delta V out? 0.6. 0.6. So my C out in this case it will comes about 16.67 microfarad. This is what the C out. So output capacitance for, you can say, desired overshoot. Output capacitance for your desired overshoot. Okay, now everything we know now. So in order to design, you can say, in order to design your buck converter. Okay, in order to design your buck converter. Okay, just wait. I will share you one PDF which is from Texas Instrument. Buck converter. Are you there? Any questions so far? Okay. Actually, yesterday I got one PDF. Okay, right now it is not there. So yes, I will share you that PDF. So shall we go for MATLAB, you can say demonstration, or shall we wait right now? And then in the next class we will design this buck converter in the Simulink model. So choice is yours. You can tell me if you go, if you continue, if you want to continue, I will continue in the Simulink. If you want to, if you want me to stop, I will stop it right now. Rupali, Kunal, Sakshi. Yes.